So I can introduce you. So this is AeroClean. But we have the same title up here that we had down here. So AeroClean Disinfectant Fogger. This is Stephen Chen, Lucy Thompson, Brian Wan, and John Yo. And RJ is, from the class of 2013, is the mentor.
Okay. So, good morning, everyone. Good morning, everyone. We are AeroClean, and we will be presenting the disinfectant fogger, which is also known as DF16. I am John.
I'm Stephen.
I'm Lucy.
And I'm Brian.
So let me introduce to you our team. Stephen is a Chief Executive Officer. Lucy is a Chief Technical Officer. Brian is the Chief Financial Officer, and I am the Chief Safety Officer. I also like to introduce our mentors, RJ Filannino, which is in the room right now, and John Show. So, a quick presentation overview. We'll be going over the background of our product, the fogger design, prototype and concepts, manufacturing process of our disinfectant solution and our fogger, the safety analysis of our factory process, and lastly, the economic analysis of the world production of our fogger. So I'll go over a couple background. The main goal of our product is germs and bacteria. Why do we want to focus on germs and bacteria? So I don't know for sure, but possibly the surfaces on the tables right now might have some residual germs. Not to scare you all at all, but there possibly could be. But for example, if you're at a doctor's office and someone doesn't clean the room properly after they treat a patient that has a common cold or flu, you may catch that after you go into the office as the next patient. And another example that influenced us was the E. coli outbreak at Chipotle. So that may be from residual bacteria and germs on surfaces that contaminate food as well. So the conventional method of cleaning surfaces right now is spraying a solution and manually wiping the surface. That could be labor intensive, time consuming, and possibly ineffective based on how well the user wipes down the surface. So our goal of our product is to minimize the time in a safe and efficient way.
So a little bit about our target market. We did a little bit of research and found that approximately $1.25 billion is spent on disinfecting products in the U.S. yearly, with an expected market growth of 4.2% by the year 2020. So our goal is to supply 1% of the current U.S. market, so approximately $12.5 million. And we're trying to develop a product that will sell for approximately $10 a unit. Our specific target market for our initial pilot plant will be medical facilities, so doctors' offices and clinics specifically. And we're going to exclude operating rooms because that requires a higher level of disinfection. And once our product has been fully developed, we're going to work on future target markets, including hotels, households, and schools.
So I spoke about what inspired us on the problem, but what inspired us mainly on the mechanism was bug bombs that utilize pressurizing a chemical solution and vaporizing a mist into an enclosed room. So our design of our fogger will be similar to pressurizing a solution into a can and also releasing it into a closed room. I also like to note that biohoods use a similar method of inoculating the hood with hydrogen peroxide, and it evaporates over time. So what makes our product so competitive is there are existing patents currently for it, but they all fell through, and none of them has been really commercialized to be safe and efficient for one-time use.
So I'm going to talk about the basis of our project. We have identified 4 design parameters that we felt needed to be addressed. Firstly, we needed to decide on a chemical solution that our product will utilize. Secondly, our product has to be environmentally safe to operate. Thirdly, we need to pair the chemical with proper materials for the product. And lastly, we need to develop a mechanism for full room coverage. So targeting our first design parameter of selecting a disinfectant solution, our initial research revealed that our competitors were utilizing alcohols, chlorines, and ammoniums. The most common chemical found was ethanol, usually in the range of 60 to 90% concentration. And this was because ethanol is widely studied and accepted as an inexpensive chemical used in bacterial and viral disinfection. Another thing to note is that ethanol is approved by the EPA and FDA as a disinfectant. Therefore, if we were to move on with ethanol, we would be able to bypass looking for their approval. Another chemical that is found is benzalkonium chloride, specifically in Lysol's disinfectant sprays. Benzalkonium chloride is also found in other household products such as nasal sprays, deodorants, and eye drops. Not many studies have been conducted on benzalkonium chloride as it's just a suspected respiratory irritant. However, it is toxic to fish and birds. So another factor that needs to be addressed, Stephen mentioned briefly, was levels of disinfection. So different levels of disinfection are appropriate for different scenarios. Just to note, high levels of disinfection require a longer period of contact time and are more appropriate for the surgical setting where, as Stephen stated, sterilization is required. Lower levels of disinfection require minimal contact time and are more appropriate for disinfecting common bacteria. This is why we have chosen 70% ethanol, specifically 70% because any less is not effective in disinfecting bacteria, and any more the contact time diminishes as it evaporates too quickly.
So a little bit about our manufacturing process. We developed some goals that we were going to focus on, specifically to manufacture our disinfectant solution in our own plant. We're going to purchase the packaging materials for the actual fogger itself from vendors, assemble the product on site, and distribute to vendors in the United States. So some considerations we have to focus on were the location of the facility, the production and material costs, the initial installed capital cost to build up the plant, the labor requirements, the target market to determine the size of the plant we're building, as well as the safety and environmental impact of the plant. And this is an overview of our main concept. Our product is going to be a disinfectant fogger that can sanitize a room quickly and efficiently. We're going to name this the DF16. Our initial target market will be medical facilities, so patients' rooms and doctors' offices and clinics. The design is going to be an aerosolized can made of aluminum with a 16-ounce capacity with 8 ounces of a 70% ethanol solution, and it's going to be pressurized with air. And our manufacturing process will be a one-directional batch production.
So this is a drawing of our design for DF16, and as Stephen said, it's going to be a 16-ounce capacity can with 8 ounces of solution, and it will be pressurized with compressed air to 90 psi, and it's designed to cover an 8 by 8 by 8 foot room. And we designed a custom cap with 4 nozzles pointed in different directions, and it will be activated by twisting the cap. And if the room is larger than 8 by 8 by 8, you can use more than one fogger to cover that area. And this shows a cross-section of the can. It contains the normal components of an aerosolized can, and we added a threaded adapter and a cap to lock it into place when it's twisted. For the packaging label, we place a warning label for ethanol because it is flammable, and we also listed the instructions for use. So first, put on all necessary PPE and turn off electronics and extinguish any flames. Close all the doors and windows to the room. To activate the fogger, first put it on a chair or elevated surface and then twist the cap and then evacuate the room. And after about 2 minutes, you can return and open doors and windows to ventilate and allow about 10 minutes to ventilate the area or until you don't smell any more fumes. We calculated the theoretical nozzle flow rate through one nozzle using the energy equation. And using this equation, we found the exit velocity through one nozzle and then used that velocity to calculate the exit flow rate. And to find the flow rate through all the nozzles in the cap, we multiplied it by 4 since there's 4 nozzles and got 0.0295 liters per second. And we used this flow rate to estimate the time it would take to dispense all 8 ounces of solution, which would be about 8 seconds.
So targeting our 4th design parameter of achieving full room coverage. We did some research on several nozzle types and their applications. So here's a diagram with different nozzle types and their respective droplet sizes. We took into consideration the benefits and drawbacks of each one to figure out which would best suit our specific application of DF16. So starting with air atomizers, which produce the smallest droplet sizes, these nozzles require a constant source of compressed air. They have a larger orifice, and therefore are less prone to clogging. Next, we have fine spray nozzles. These generate a larger droplet sizes than air atomizing nozzles. The benefits of these nozzles is that they have simple installation, they have low operating costs, however they have a smaller orifice, therefore more prone to clogging. Following that, we have hollow cone nozzles. These generate a ring spray pattern and are mostly used in dust prevention. Then next we have flat fan nozzles. These generate a rectangular spray pattern and are mostly used in dust suppression. Lastly, we have full cone nozzles. These nozzles generate a circular spray pattern with uniform coverage, and these nozzles generate the largest droplet sizes. With the larger droplet sizes, particles are able to maintain their velocity over a relative distance, and for our specific application of DF16, we require a nozzle to not only have uniform coverage, but also carry the particles to make contact with the wall. Therefore, full cone was our best selection. So continuing on with the full room coverage, DF16 has the responsibility of coating a 8 by 8 by 8 foot room. This has a surface area equivalent to 384 square feet. So the optimal position for DF16 would be in the center of the room, where it is equidistant from every wall. We did some research and we found equations specific to full cone nozzles that would dictate the theoretical spray coverage. So assuming that the particle would have to travel a distance of 4 feet, half the dimension of the room, to make contact with the wall, and that the spray angle would be 90 degrees, assuming one nozzle is pointing at each surrounding wall, we would have a theoretical spray coverage of 8 feet, which is the dimension of the wall. Therefore, theoretically, we have a full room coverage with this setup.
So in order to test the effectiveness of our product and our solution, we conducted a pilot study where we tested a prototype of DF16 in a bathroom that's approximately 8 by 8 by 8 feet. And we swabbed the surfaces before and after. We activated the fogger in the bathroom and grew cultures to compare the bacteria count. And in addition, we also determined the evaporation rate of 70% ethanol solution at room temperature to give us a better idea of how long it would take for the solution to evaporate out of a room. So this shows the setup of our test. We purchased a rechargeable 16-ounce capacity, max pressure of 90 psi aluminum aerosol can, and we filled it with 4.8 ounces of solution because we didn't have enough ethanol to do the full 8 ounces. And we pressurized it with a bike pump and filled it with compressed air to 90 psi. And we also added red dye to the solution to increase visibility when we sprayed it. And we 3D printed the cap design and also the threaded adapter to test it with our prototype. And this is a picture of the culture kit we purchased with LB agar plates to grow our bacteria cultures. This picture shows the spots that we swabbed in the room. We did the door, the wall, the floor, and the toilet seat because we thought they would be areas that there would be a lot of bacteria. And this is a video clip of our fogger test. So it had to be held down manually because the adapter was printed a little too small so it wouldn't lock into place. So it's like held manually throughout the test. And you can see the solution's colored red, so you can kind of see the spray pattern. And I observed that the spray was coming out of all 4 nozzles, but it seems like it's more concentrated going toward the door. And there was also a little bit of leakage because there was a small gap between the valve inlet and the cap, so there was a little bit of room for solution to escape. So these are the results from our prototype test. We measured a pressure drop of 65 psi, and it took 45 seconds to dispense the 4.8 ounces of solution. And this is, we determined a flow rate of 0.003 liters per second and used that to estimate it would take about 1.25 minutes to empty a can filled with 8 ounces of solution, which is greater than the theoretical calculation for the amount of time we thought it would take. But that might have been due to a lot of the leakage and pressure loss. And we also measured the evaporation rate of 70% ethanol solution, and we filled a little dish that was about 2.5 inches in diameter with 15 mils of the solution, and recorded the mass every 5 minutes for 45 minutes. And we plotted the results here, and from the slope of the line, we determined the evaporation rate was 0.0355 grams per minute. And from this rate, we used this to get a rough estimate of the time it would take to evaporate 8 ounces of solution if it was dispersed evenly in an 8 by 8 by 8 foot room, which would be about 0.367 seconds.
So, as you all been waiting for, the pilot study results. This is our kitchen sink control. We did this to first verify that our agar plates were working successfully before we actually performed the study. So the image on the left shows our pre-floor to post-floor. As you can see, it went from 250 colony forming units to 55 colony forming units, which is approximately 80% less bacteria after using our prototype DF16. So the image on the right, you see the pre-wall to post-wall. It went from 10 colony forming units to 0, which is 100% killed bacteria after using our fogger. So based on Lucy's video, we also observed that it clearly hit the door, and it didn't really reach the toilet seat. So based on this image on the left, the pre-door to post-door, we can assume that there wasn't really any germs on the door to begin with, so our fogger didn't make much of a difference after using it. And on our pre-toilet seat to post-toilet seat, both of the agar plates look very similar, so we can assume that if our fogger does hit their active surfaces, it's very effective. So going over the supply chain flow diagram, our company will first purchase raw materials, form our solution through a factory process, quality check our 70% ethanol, assemble our device, field test it for success, and then market our product at a convention, hopefully attract enough investors for a world production of DF16.
So going a little into our manufacturing plant, we decided our plant would be located in Fujian, China, because it's really currency enabling. There are cheap utilities, easy access to raw materials, since most of our vendors will be from China, and lower manpower costs overall. The process is going to be batch process. We're planning on producing 4,808 foggers a day in order to meet our target market goal of $12.5 million. This is approximately 1.25 million foggers a year. The plant will operate for 24 hours a day for 5 days a week with 3 8-hour production shifts per day. And a little bit about our manufacturing process itself. We're purchasing the raw materials, which will be the ethanol, QC checking that before pumping it into our feedstock storage tank. The water source will pump water into a distiller that will purify the water into our feedstock storage tank for the water. And they'll be pumped at an appropriate ratio into the mixer where the product will be made and before being pumped into the QC vessel, where our final product will be QC checked before assembling it into the final fogger. So this is a list of our main equipment that we're purchasing. We're buying an ethanol purity analyzer for the initial purity check, a 1,000 gallon per day reverse osmosis system to purify the water, a 3,000 liter industrial mixer, a aerosol can filling machine that fills the cans at 60 bottles per minute, and 3 300 gallon feedstock storage tanks for the ethanol, water, and final formulation. Our material balance was relatively simple. We're assuming that there's no generation, consumption, or accumulation in the system. So the first stream is the ethanol. It flows in at approximately 1,900 liters a day. The water tank will flow at approximately 800 liters a day. And then the mixer will develop the solution at 2,750 liters per day.
So I'll go over the piping and instrumentation diagram. I like to note that all the tanks, valves, and pipes will also be stainless steel grade, mainly to avoid any type of corrosion over time, because we'll be utilizing 99% ethanol. I also like to note that we have pressure sensors, level sensors located at all major components of our factory process, mainly to ensure that there's no hazards that will occur and safety of our workers. So speaking of more safety, as I mentioned before, our main chemical in our factory is ethanol, mainly because it's dangerous mainly because of its flammability rating of 3, boiling point of 78 degrees C, flash point of 63 degrees C, and auto ignition temperature of 363 degrees Celsius. So, like I said, we are diluting the solution to 70% ethanol concentration in DI water, so its toxicity level will be relatively low, and our corrosion rating will be also low. However, in our closed batch system, we will also have safety features. We'll have high ventilated rooms to ensure that any excess ethanol vapors that are in the room will actually be ventilated out very quickly. We also advise our workers to wear proper PPE when handling this chemical. So here's our process failure mode analysis. We chose 3 major components in our factory process: the mixer, the distiller, and the compressed air tank. The failure modes that we were going to assess is crack in tank and crack in the glass. The effects that due to these failure modes would be ethanol spills, flooding, and a decrease in pressure of the tanks. Potential causes would be corrosion over a long period of time. Like I said, we're using stainless steel grade materials, so it will take a while, but we still take these measures. So we have process controls, like I mentioned before, in the PNID. It'll be level sensors and pressure sensors at these major components and operating at a specific range. So if there's a range that, if there's a pressure level that operates outside its range, then the system will come to emergency stop to ensure the safety of our workers.
So a little bit about our economics. This is the list of the main equipment that we're purchasing. The costs initially are relatively low, with the most expensive thing being the aerosol can filling machine. But we also have to focus on the maintenance of this equipment as we go on. For our raw materials, we're purchasing 99% food grade ethanol at $1.10 per liter. We found a vendor for aluminum aerosol cans with already pre-assembled valves that sells the cans for 90 cents each. But since we're buying in bulk, the cost may probably go down. And we're also purchasing caps with our design from a company for 10 cents each, and that's made out of plastic. And our total yearly cost for raw materials will be $1.8 million. For our utilities, we found the price of electricity in Fujian was 8 cents per kilowatt hour, and the cost of water was 23 cents per cubic meter. We determined our yearly usage of electricity and water, and found that the yearly cost would be around $50,000. For our manpower, we're hiring for 4 positions, including the fluids processing technician, the quality control analyst, the packaging specialist, and the shipping and receiving. The fluids processing technician will focus on the mixer as well as the feedstock storage tanks. The quality control analyst will test the ethanol as it comes in, the water as it's getting purified, as well as the final product of the formulation. The packaging specialist will work on the final assembly of our product.
So continuing on with the economics, here is a table of our cost of productions. We estimated that $25 million will be sufficient in covering our startup year of process needs. This value is based on a variety of factors, such as the need for construction of our manufacturing facility, further product research, need for shipping of equipment, and lastly, marketing fees. Because our only chemical is ethanol, our environmental charges are going to be less than other chemical plants. And our running license is going to be below global market average, as land in China is cheap. Totaling our other parameters, we come to a total of $5.6 million, and this is an estimate plus or minus 40%. These numbers will be more concrete once we begin our starting phase of construction of our manufacturing facility. So here's a pie chart depicting our yearly spendings. Just to note that maintenance, environmental charges, cost of raw materials, and capital charges are our larger contributors. If opportunity arises, we will seek other suppliers for our raw materials at a more competitive price. And again, just to reiterate, these numbers are subject to fluctuate once we begin our starting phase of construction of the manufacturing facility. So for our annual gross margin, we had to make some big assumptions. We assumed that our raw materials, cost of production, utilities, and raw materials would be constant over the next 7 years. If that's the case, we plan on bringing in $5 million annually. With an interest rate of 6%, we plan on paying back our investors in full within 7 years. As the Chief Financial Officer of AeroClean, I believe that it's imperative we accelerate that process, so we will be taking a majority of our profits and reinvesting that back into the chemical plant. That will allow us to increase our capacity, increase our production rate, and also attract more potential investors that will help see the growth of AeroClean as a company. So just to sum up the other assumptions we have for the project, the first major assumption was that the US disinfectant market is $1.25 billion and that AeroClean itself will be able to supply 1% of that market, because that really set the production rate of our facilities and really dictated how much chemicals we would need daily. Moving on to our prototype, we assumed that there'd be no pressure loss for the nozzle flow calculations, and as Lucy described in the video, it wasn't a really accurate representation of our design because there were some leaks and there was some leakage at the valve cap interface. And lastly, for the frictional loss between nozzles, we assumed that it was negligible, and that was obviously not the case, as again in the video there was not a total room coverage, it was more concentrated at some points. So just to sum up the vision we have as AeroClean, we saw an increasing need for the general health to improve after several outbreaks such as E. coli at Chipotle, and the current methods in place are not as effective as they are as there are height limitations. They place users at a moderate time of risk, and it's also not an effective use of their time. After a successful launch of DF16, we will be able to see a healthier environment. Staff members will have their time free to focus on patients, and we will be able to increase our target market to really capture the household environment, which is our goal.
So for our recommendations for future product development, we're going to work on improving the seal to prevent the leakage of the solution by forming a tighter cap between a tighter fit between the cap and the valve inlet itself. We're going to try and optimize the flow of the cap design to decrease the frictional loss by changing the size of the nozzles itself in the cap. We're going to work on trying to fix the locking mechanism that we couldn't get to work in the prototype. And we're going to investigate future fiber capacity options to increase the coverage area of the fiber itself.
We'd like to thank our mentors, RJ and John, for all the help and feedback throughout our project. And we'd also like to thank Professor Webster and Professor ChE and Canny for his help in the lab. These are our references. And that concludes our presentation. Thank you for listening. Are there any questions?
I have a bunch of them. You showed, I think slide 29 or 30, a distillation unit, but it didn't show up in your plan. Good. 29. In the process flow, there it is. Oh. Didn't I see distiller? I didn't see anyone else for one.
That was actually the lowest osmosis system.
Okay, so it's misled here. You can fix it. The major issue I had, I think, was the flash point of 70% ethanol, which you said was 68 degrees C or something. If my recollection is correct, National Fire Protection Association, NFPA, has flash point much lower. And if I remember correctly, 20% ethanol in water is somewhere around 70 degrees F. So I think what you could be doing here is generating an explosive aerosol in a room so that a thermostat or a light switch, because you're not dealing with explosion-proof rooms, could blow the walls out. So I would urge you to go back and recheck what the dangerous limits of ethanol vapors are. And I tell you that from experience in biotechnology, that everybody uses 20% ethanol to wash down surfaces, and you have to be very careful with it because 20% won't pass the fire code in most municipalities. But you've got 70% and you're aerosolizing. Worst of both.
Yeah, so what do you think you could do if you find out that there's a problem with the concentration of ethanol that you want to use?
Even the ethanol spray coming out of the can could generate a static charge and cause a spark. And that's enough to ignite it.
Well, in our IFUs, we instruct the user to like unplug any electronics, make sure there's no open flames, so
I heard
like it will
that.
decrease the risk of that happening.
There's a light switch in the bathroom. There might be a thermostat, like there is in my bathroom, which operates automatically. Most people don't know how to shut them off.
Again, this product is not really intended for the household environment as of yet. It is more intended for healthcare facilities that we will be able to also put that on our instruction label to cover said circuitry as well to avoid that from happening.
What prevents me as a consumer from taking it or somebody else and consuming the ethanol, since it's not denatured ethanol?
Yeah, maybe thinking more globally, how important is ethanol into your process? Are you married to ethanol in this process? Could you think of other cleaning solutions, or could you think of a different approach maybe that could get past some of the issues that are being mentioned?
As I mentioned before, we were looking at hydrogen peroxide because it is used in biohoods as of today, but ethanol is currently what we use in our DF16, so that was some of the results.
The advantage of ethanol is it's not particularly toxic, whereas it doesn't damage a lot of things the way that peroxide will. And chlorine dioxide is another means of sanitizing or sterilizing surfaces. Again, it's more complex. It's not for general use. You need that to seal the room.
Yes.
Did you test the economics of shipping your products from China to the U.S. market against your decision to site the plant in China?
We did not specifically look at those shipping costs, but it is in our favor that we set up a plant in China, as it is currency enabling. But we believe that.
But currency enabling is, I mean, that's money. It's there's an economic cost of getting your product from where you're making it to where you want to sell it. And if you're making a siting decision based on saving money, you left out a big test, which is what's it going to cost to ship it to the market and distribute it. So, I'd say you could assert that it's going to save you money, but you should have proved it, I think.
Okay, we can definitely go back and do some research on that topic.
So I've loved the pilot study because I think you learned a lot from doing the pilot study, and as you know, one of the things we're trying to do in this design course is more hands-on design. So I wonder if you could summarize what you learned in your pilot study, and if you had to do your pilot study again, how would you do it better?
Well, if we had more time, we would have liked to build like an additional prototype or like reprint the parts again to test it again, because like there's definitely revisions that could be made to both the cap and the adapter, and yeah, if we had more time and resources, we would have liked to try that.
Anything else?
From the safety point of view as well, I mean, after mentioning how dangerous, and we would also definitely do it at a home house and kind of take the circuit breaker off so there's no electricity in that certain room that we'll be testing, and then they'll be avoiding any type of like potential explosions that may occur.
I did a quick lookup, and flash point of 70% ethanol appears to be about 17 degrees C,
Yep.
62 degrees F.
I actually changed that this morning, and I think it was a bad Google. It was actually originally at 23 degrees C, and that was supposed to reference our 99% ethanol, and it was a wrong Google change. Yeah, I apologize.
Very dangerous.
Yes, it is.
So is
It's very
Wikipedia.
Yep, I believe it was from Wikipedia source. That was the first thing that I said.
But using multiple sources
Yeah,
for
using-
information,
yeah,
right, is the key.
So that's what made me second guess. I originally saw 23 degrees C, and then I saw
bet Terry's would
68.
have it.
So it got me very second guessing myself, and I changed it like literally this morning.
I think the other thing in your pilot study that would have been great to include was a control. So you had a control in which there was no treatment, but a control in which people clean surfaces today in hospitals. So in my office, I actually have the wipes that they use in the hospitals. And to wipe that across all your different surfaces and then do the cotton swab and determine colony forming units would have been great to see. And I think what you would have found out also, and you alluded to this in your presentation, there was a lot of human error in cleaning surfaces that I believe you're trying to get around by not having, you did have some human error in your pilot study, but if it was perfected, you wouldn't have the problems that hospital care people have when cleaning surfaces just due to human error. So I think that would have been a great thing to include in your pilot study too.
One more thing just to be wary of, when you go from 10 colony forming units to 0, you're not sterilizing it, you're not getting rid of 100% of the bacteria, you're reducing the load by 1 log. Because if you had 10 to the 6 bacteria per square centimeter on that toilet seat, would you still get 0? Or would you get something more? And you don't know the answer. So the limit of your experiment was 1 log reduction. But that still shows, it's a good indication that the system works. It does a lot, but you don't know how much yet.
That's very true.
I think it's great that you guys did both a process and a product design. I think it's awesome that you took on that challenge. Where do you think, in scaling this up and commercializing it, the greatest technical challenge is? Is it refining the product? Is it the manufacturing process?
Probably like refining the product. We want to make sure that we have something that works well, and so it requires like a lot more R&D and a lot more testing, and so probably that. Yeah, because our process was like fairly straightforward, I think, for our manufacturing.
What aspect of the product design do you think is the most technically challenging?
Probably like the calculations and making sure that it will like cover the entire room that we say it, or the entire area that we say it will, and like reach all the areas. So we want to make sure that our product is effective.
I also think choosing the solution is a very big key, because I recall that there are patents for disinfectant foggers, like I mentioned before, and mainly why they fell through was because of safety. So our 70% ethanol is currently still dangerous, and people may have tried to use this as well as like the benzalkonium chloride and all that dangerous substances, which is why patents are submitted but have never really passed for commercialization.
I think fogging's a great idea.
Yeah.
You have to be careful what you're fogging with.
You didn't show off your
Oh, we also brought in
People.
our prototype that we tested with. It's a little dirty.
So
but-
what pieces were printed?
The adapter, like this was the second version. The first one was too big, and then this one was too small. And we were testing that day, so didn't have a chance. And then this is the cap. It's the same design that we showed earlier, and we 3D printed it. Yeah, in plastic here. So.
Any final questions for AeroClean? Yeah.
What would that cap be made out of in real production?
Plastic.
What type of plastic?
Polypropylene.
Yeah. Like that.
All right. Very nice. I feel clean even just listening. And on fire at the same time. So thank you. That was really, really nice. Thank you.